Hi everybody. So I'm going to try a new recording setup here. This is what Colleen recommended. So I'm just trying this out. So we'll see how well this works compared to me talking at the board in my living room. I just wanted to mention a couple of things as we head into today's lab, which is Pendulum Procedure Part A. So first, a few logistics things. I just wanted to clarify what is going to be due next Tuesday for this lab. There are several things. So first of all, based on today's experiment, I'd like you to turn in a graph of your data, of the data we take for procedure A. Uh, so this can be either hand-drawn or electronic. Um, I would also like you to turn in a paragraph where you assess whether the model describes your data. These two items are listed in the lab manual under section 6.2.3 on page 33. You don't need to turn in a data table because we're all looking at the same data. The other thing that's going to be due for Tuesday is homework for Pendulum A, but only questions number 1 and 2. I went through question 3 in detail in the lecture that I posted for Tuesday's class. So you should know how to do that, but I'm not going to ask you to reproduce that on the homework. So just number 1 and 2 of Pendulum homework A. So just one thing about today's goal, right? So we have a model for the behavior of the period of a pendulum at small angles. So we have a model for period t at small angles. Namely, right, we said that t equals 2 pi times the square root of L over G. So a few things to note here. So, right, so note that it is interesting to note what this doesn't depend on. So there's no mass dependence, right? And then no dependence on release angle, which I'm going to call theta naught here. So what this does predict, though, is that it does the period depends. So it does depend on length. And that's what we're going to be checking today. How we're going to do that is, once again, we're going to linearize this model. Right? So, and I can do that if I square both sides of this. So if I square both sides of this equation, my linearized model goes like t squared. If I square 2 pi, I get 4 times pi squared times L over G, right? Or if I just rearrange my constants, I get 4 pi squared over G times L equals T squared. So the implications here, are the following, right? We're going to want to plot T squared versus L, right? So if this model is in fact valid, so the data should be linear. Data should fall on a line, right? The slope should be plausible, right? And the slope here is, in fact, this thing in front of the L, which is 4 pi squared over G. And as you can see from this equation, right, t squared is like y and L is like x. There's no intercept here. So we should have a y-intercept of 0. So let's go ahead and look at the experimental setup, and then that's what we'll be checking this week in procedure A, as we will measure the period for a whole bunch of lengths and see what happens.